Hello CIO world, and welcome to another installment of heat transfer. In this session, we will be continuing with steady state conduction, expanding on what we have learned previously. And if you hear any chickens in the background, please just ignore them. This is quite a long session, and we will cover a lot of work. So what we will do is revisit resistance again, which we already know from the previous module, and end off with thin surfaces as well as special configurations that help us look at heat transfer, solve problems in a intuitive way. So let's begin. In summary, heat transfer is promoted by two main principles or properties, namely the temperature gradients as well as the thermal properties of substances. It is useful to think of this in terms of electricity. On one side is a high concentration of energy in the form of electrons relative to the other side. What determines the rate of flow has to do with the properties of the pathway. It is not just simply energy potential that drives the flow of electrons, but also the conditions of the pathway through which the electrons must flow. So, for example, the tungsten wire is not as effective as copper in conducting electrons, but the tungsten wire also has a really tiny cross-sectional area through which the electrons have to flow. So what happens if you place a piece of glass in the path? Well, no flow. So just as with a battery, heat needs some sort of energy gradient, and this comes about due to a temperature difference across the pathway. And we can therefore say that the temperature promotes energy flow, where the gradient is proportional to heat flow. The path also provides resistances along the way to energy flow, where a longer path, for instance, results in a lower flow rate. And the path length or the pathway is set to provide resistance to heat flow. Now, thermal conductivity counters this, where a higher thermal conductivity will promote better heat transfer and vice versa. And lastly, if we look at area, the cross-sectional area, specifically if this area is large, then it will also promote heat transfer. Now, another way to look at these various terms or properties or dimensions, geometries, is how they affect the resistance to flow. So we often like to talk in heat transfer about resistances to flow. So just as a resistor in an electric circuit would cause resistance to the flow of electrons. So consider then these three properties of the flow path as entities that would cause some resistance. Then we can arrange our conduction equation to reflect this principle as shown here, where the denominator is referred to as the thermal resistance of heat flow in this instance. Now let's consider the following circuit, and starting from the one side to the other or in the middle, we can describe this sort of heat transfer as a circuitry of resistances that we add together. So let's do this. At the steady state conditions, we apply the good old energy balance as shown here. So just remember, in minus out equals generated plus consumed. Don't forget the energy balance. I know you've done it many moons ago, but as engineers you must always continue to use energy balances as well as mass balances. So generally, for these types of networks, we seldom know the intermediate temperatures. So for example, we may know the temperatures of the cold and the hot fluids that are flowing through a heat exchanger, but not necessarily the temperatures at the interfaces, so where the fluids have some or other solid boundary between them. Okay, so we might want to know these. Also, at times, if we are working with opaque fluids such as water or other fluids that are not necessarily very hot, then we can neglect radiation. Okay, it's only when we have something like a gas or a vacuum that radiation plays a significant role, and if the temperatures of the surfaces that are doing the generating of the radiation particles are hot enough to do so. Right, so to the left of our diagram, we have resistance due to the limitations of convective heat transfer to transfer energy. And in the middle, we have the thermal conductivity, the length, and the area through which heat must flow, which provides additional resistance to conduct heat through the body or through the substance. And similarly, we also have convective resistance to the right-hand side. And just like in an electric circuit, we can sum up all of these resistances in series, as shown here. Okay, and we can then substitute this result into our energy equation. So nice and simple. Now, another way of looking at this is as follows, where since we are operating at steady state conditions, in this instance, we can equate everything as shown here. All right, so if we sum up everything, we eventually can cancel out certain terms, specifically the energy, the intermediate temperatures. Okay, and then we can determine heat flow. So in this case, this equation is very useful if we want to know how much heat in watt is flowing through the different interfaces. And yet again, we have a typical resistance circuit which we obtain in this instance. Now consider the following example. You may pause here for now and read through the problem statement yourself, and specifically take note of all the important bits of information which are highlighted here for you, namely the dimensions used to determine the area that is perpendicular to heat flow, the thermal properties of the solids, so there are two of them, as well as the fluids that are playing a role in heat transfer, and also what questions need to be answered specifically, as well as any boundary conditions that are given to you. Now, after considering the assumptions and the analysis has been completed for this problem, we approach the solution by determining the resistances first. And these are easily computed, and their sum is given as follows. The sum of the resistances is equal to 0.4332 degrees Celsius per watt. And always remember to put your units. All right. And then we obtain, the following result for heat transfer, and we end up with 69.2 watts. Okay. For the specific geometry. Obviously, if we increase the surface area, the wattage would increase. If we increase the length, the wattage would decrease, and so forth. We can also then, answer the second part of the question, which asks us to determine the intermediate temperatures. So once heat transfer is known to us, we can then set up further equations at the intermediate positions and use the intermediate boundary conditions. And we can calculate, for example, T1, which is equal to 14.2 degrees Celsius in this case. Okay, so here we had a gap of air. Okay, so we had an air gap. But instead of this air gap, what if we had an imperfect contact between two solid materials? The total energy transferred then across the gap would equal the energy transfer through the area of direct contact plus the energy transferred across the gaps. Now, what would this look like mathematically? Do we know what the area for the contact points are? Do we know the area for the gaps? Not necessarily. Typically, these are very microscopic. So we need another way to determine these. Unfortunately, very clever people have come up with a way. So what we do is we use the form of Newton's rate equation and determine a new property for the gap called the thermal contact conductance. Okay, and this includes both of these contact and gap heat transfer entities. So we may use an example to illustrate this type of heat transfer further. So have a quick read of the problem statements yourself and let's unpack it together. So we are told what the thickness of the aluminium plates are typically. We don't necessarily have to be told this. And we are told what the measured thermal conductance is. This is the HC. And we are asked to determine the thickness of the aluminium plate that would have the same thermal resistance as if there were no gaps. So we are asked to consider the case where we do have this thermal contact resistance, okay, due to a gap between two plates, and we are asked to calculate an equivalent thickness of an aluminium plate as if there were no gaps. In other words, that we were just working with one plate instead of two. So, did you catch this? Okay, so think about what is being asked. So by definition, the resistance across the gap is given to us as 1 over Hc, right, which we can then calculate to be 0.909 times 10 to the negative 4 meter squared Kelvin per watt. Okay, so remember your units. The resistance can have different units depending on whether you are given the area through which heat is being transferred or not. Okay, and next we define the resistance of an aluminium plate. Hypothetically, if we just had one aluminium plate, this is what its resistance would be, where the only unknown to us is the length of the said plate. Since K, the thermal conductivity of aluminium, as well as the resistance for the aluminium are known to us in this case, okay, we've already calculated what the resistance should be with the previous calculation where we used 1 over Hc. Then we can calculate L, and L is then equivalent to 2.15 centimeters, so almost an inch thickness. Right, so that is the answer. Now, various contact conductances have been measured for us and reported in the literature. You can find this in many books, and the textbook gives its own. So notice that surface roughness is used here as well. And this is something that we have seen already in piping system design. Next, let's take a quick refresher on insulation again, but remember that we have already known this from a certain module that was completed recently enough to recall all this information. For this analysis, we define the heat flow from an insulated pipeline due to convection. This pipe can be hot or it can be cold, it really doesn't matter. And we consider what is the relationship between this heat flow to or from the pipe due to the thickness of the insulation material being used. So to complete this analysis, it was useful to define a thermal resistance as shown here, and therefore we can specify resistances due to the insulation as well as the surrounding air. So this is conduction and convection. We obtain the following from summating these resistances, which simplifies to the following form. So the question was, what happens if R3, which is the radius or thickness of the insulation material, what happens if we increase it or decrease it? We note that two things can happen. Either heat transfer can increase or can decrease, but when will either happen is the question. So to find this out, we take the derivative and find out where this derivative is equal to 0. And it just so happens that this derivative is equal to 0 when R3, which is the critical radius of insulation, is equal to K2, the insulation's thermal conductivity, as well as H, which is the convective heat transfer coefficient for the surrounding fluid. It doesn't have to be air, it can be rayon, it can be radon, I mean. It can be nitrogen, it can be CO2, etc. And we know that this is where heat transfer reaches its maximum value, and any increase will bring about a decrease in the heat transfer and thereby insulating more and more effectively. And we looked at a previous example to illustrate this principle, which shows that the critical radius is actually quite small. And in general, we typically use much thicker insulation materials in any case. They won't be 2 millimeter. They will typically be maybe 2 centimeters or 5 centimeters or 10 centimeters and even larger than that, depending on the application. Just before we get to finned surfaces, let's also just quickly recap the last few concepts that pertain to resistance, to heat transfer. If we have resistances in parallel, for example, as shown here, we define the resistances mathematically, and look, those resistances that are in parallel can typically be approximated in the same way that we do so for electric resistances that are in parallel. So this will be the green and the purple computations here, or yeah. Okay, but always we typically end up with the same form of our equation regardless. And keep in mind though that you must understand where this equation comes from, how it was derived. This is very important. Don't just use equations blindly. Know what their uses are and know their limitations. Or else you may make very bad assumptions or oversimplifications and land up in hot water. So, lastly, however, that being said, the main reason why we go for this form is that later on we will want to define what is known as the overall heat transfer coefficient, U, when designing heat exchange equipment. Now, the overall heat transfer coefficient is useful to us as it can actually be determined experimentally. We run two fluids, past each other through heat exchange equipment, and we determine how effective is the heat transfer. And we can therefore determine what the overall heat transfer coefficient is. We run a few tests at different flow rates, etc. We will get into the design of heat exchangers shortly, but it can be determined without knowing actual properties or thermal boundary layers, gap resistances, or fouling for that matter. Often we can approximate fouling resistance. So this is where the pipes tend to create layers over some period of use. Maybe it is calcium scaling, etc. And these can also be determined and factored in when you design a heat exchanger. Design it just slightly larger for larger surface area. Although we still need to make sure that we can design this and make good predictions so that the equipment that we have designed can actually work in the intended way. We need to obviously understand all the aspects of determining these. Right, so know where the equations come from, know what the symbols imply about the design. So let us now talk about fins. What are fins? They are not something that are on fish. They are also something that is in your computer and your cell phone. Think about fins as an increase in surface area through which heat can be converted or convected away, etc. So it's conducted through the fin and then convected over the fin surface into the fluid in question. So the more surface area that I provide or that I have, the more heat or the more energy can be dissipated. Alright, so the source of the heat is the hot surface, and this provides like a sink, and then the heat then travels through the fin and gets convected away. So in principle, let's say that we have air or whatever other fluid. In principle, the additional surface area adds to the heat transfer. So to determine the effective heat transfer area, we need to measure it. So consider the parameter of the fin as shown here by T and W. And what we are really looking for is to define this A in the following equation that is shown here in green. The area here is delta X times by T. So that's just the one rectangular surface area. And note that there are obviously two of these, one on either side. The same goes for the top and bottom areas, which are also delta X times W per area. The total area, therefore, with respect to all the small elements that we are now analyzing, so this is in just the red section, is delta X times by 2 times the sum of the sides with lengths T and W. So realize that this is actually, in fact, the perimeter of the fin, T plus W plus T plus W. Right. Therefore, we can substitute in this area into our equation as shown here, and then add this to the total heat balance. And we rearrange the equation, and we see that we have a possibility of taking a limit. Okay, so that is what we do, and we end up with dq conduction dx plus a convection term. And since we know that the conduction heat transfer Q is equal to negative K times A times dt dx, we can substitute this into the equation and obtain a linear homogeneous second order differential equation. Oh, what fun we are going to have. One of the properties of the equation is that we can define area however we want to for different types of geometries, and we also have certain properties, thermal properties. So there's the perimeter, there's the convective heat transfer coefficient, and there's the thermal conductivity in question. If you have ever seen fins before, so this is just a model of a fin. So what fins typically look like, there are different varieties of design, and there are so many that one can choose from, and they all are trying to achieve some or other form of heat transfer. So this equation takes on a particular form, which several types of solutions can be obtained. All right, and it's based on these different solutions that we obtain the different designs in the fins. So let's have a look at this in more detail. You should read up about this more in the textbook. It gives you a full exposition, and you must be sure to understand the section, as it will really become tricky if you don't fully understand it. So it will be detrimental to the application when you're busy doing your tutorials or doing any exercises for assessment. So what types of boundary conditions can you think of that could possibly help us to come up with a particular solution, or 2 or 3 or 4, to this differential equation? So firstly, consider having an infinitely long fin. Obviously this is not possible, we can't reach infinity, but just say that you design this fin to be incredibly long. It's really sticking out there. The equation that describes heat transfer from such a fin is described as follows. It's given to you in the textbook, and so you don't have to learn this. You just have to turn to the right page in the textbook and then see what it well, you obviously have to first look at assumptions and analysis, and then decide for yourself, okay, I am dealing with a case where I can treat it as an infinitely long fin. So just remember that we apply this equation for fins whose tips are close to that of the surrounding fin, the temperature. So if the fin's tip is kind of close to the temperature of the fluid, then we're probably dealing with a infinitely long fin. So the fin doesn't need to be infinitely long. If a fin is really narrow, in that the surface of its tip, the area of the tip that faces the Z direction, is so small, and it's so much smaller than the area of the rest of the fin, the cylindrical surface area of the fin, then we can treat this fin as having an adiabatic tip, because the heat transfer out of the tip is so much smaller than the heat transfer radially out of that fin. And so we can apply the following equation. Now, the third scenario is a fin whose tip is at some known temperature. So if I know what the tip of the fin is, then I can just go with this temperature as well for a more accurate description of what is happening in terms of heat transfer. And then the last scenario is if we have a significant convection at the tip of the fin. Try to look at this equation. I just want to stop here for now and decide for yourself what will the effect be on an increase in convective heat transfer, or rather, if you have a high convection, if you have very high velocities, fluid velocities passing the fin, will this increase or decrease the efficiency of the fin? We will get to these sort of definitions a bit later, but just keep that in mind. Right, so, this last equation is quite a complex one to solve. So let's see if we can simplify it just a bit more. One way, a very clever way to do this, is to pretend to extend the fin so that the additional surface area created equals the surface area of the fin tip. And by doing so, we say that we have created a corrected length to account for heat that would leave the fin tip. And imagine that all the heat leaving the surface of the fin instead leaves only in the radial direction. None of it leaves in the Z direction. This reduces the complexity significantly, since we can now approximate heat transfer by using the adiabatic model instead, albeit with a corrected length. And there are correlations to calculate this corrected length. Note, however, that we define this corrected length in dependent, and it is dependent on the type of geometry in question. So, for example, rectangular geometries will have a different calculation that you should use from cylindrical geometry. So just keep that in mind. Okay. You must also be asking yourself now, if there are so many options to choose from in terms of designing different fins, different geometries, how do you go about designing fins to operate correctly? So first off, two concepts that should be considered are the fin efficiencies and their effectiveness. So how effective is the fin and how efficient is the fin? There are heuristics that we use where we say, well, we will cut off efficiency to no less than 60%. Where most fins are designed to operate at a 90% efficiency. How effectiveness should the fin be? Should it be 5-fold? Should it be 10-fold more heat transfer, as in the case with no fins? So there are heuristics that you can consider as rules of thumb, and use this not as a rule, but just as a guideline. Right. So let's first understand, what do we mean by fin efficiency? Think about the rate of heat transfer from all positions on the fin if the fin was at the same temperature, 80 degrees Celsius throughout the fin. This would be the ideal case because the temperature gradients are all very large and are the same across or throughout the fin. Now consider if we dropped the temperature across the fin so that those parts which are furthest away have a lower temperature gradient to utilize for heat transfer. Now the question is, how is this rate of heat transfer now affected out of the fin, or from the surface to the fin and then to the fluid? This is the real case. Now, by definition, efficiency is the ratio of these two cases, the ideal case versus the real case. In other words, rather the actual heat transfer divided by the real heat transfer, or the ideal heat transfer, my apologies. So what you look at is how much heat transfer am I transferring, and how much heat transfer could I ideally transfer out of the fin. Okay, I get my words mixed up. So just pay attention. Actual heat transfer versus ideal heat transfer in this case. Right, the efficiency calculation for a long fin and an adiabatic fin is determined thus. These equations are given to you in the textbook, and once again, you don't have to learn them or derive them. Just understand how they were derived and then use them accordingly. And also remember that M in this case refers to the convective heat transfer coefficient, the perimeter for the particular geometry of the pin or the fin or the plate fin or whatever you are working with, divided by its thermal conductivity times by the area, the corrected area for that fin. Okay, so just think about, remember what M refers to. Think about what happens with M and also M times L if we increase the length more and more. So, the question really becomes, can we design fins that are really, really long? What is the effect on efficiency? So the question is answered by a unanimous no. We cannot. There comes a point where the additional lengths added up to a redundancy. All these additional lengths to the fin become redundant since they have a negligible effect on the heat being transferred. So for instance, for an infinitely long fin, L is said to equal 5 over M, okay? And it transfers just about all the heat that it can. But if we were to halve this length to L equal to 2.5 over M, so we've halved the length, this only reduces the heat transfer by 1%. So what a waste of material here, wouldn't you say? I mean, this is not very efficient. So just by removing half of the material, we don't even drop the heat transfer by 1%. Okay, next let's take a look at a slightly different concept called the fin effectiveness. So how effective is the fin in increasing heat transfer from the solid into the fluid that is surrounding it? Consider the difference between having a fin and not having a fin. What is the impact? So what does, what impact does the addition of a fin have to heat transfer? So the effectiveness is therefore defined as the rate of heat transfer with a fin versus the heat transfer without a fin. So heat transfer without a fin is simply the convection from that surface. Okay, so remove all the fins, calculate the heat transfer via convection off of the surface. And on further inspection, it can also be shown that the effectiveness and the efficiency are related to one another. And so once we've calculated the fin efficiency, we should be able to calculate the fin effectiveness as well. So if you have a question, calculate fin effectiveness, then I should also calculate efficiency first. This is going to make life a lot easier. For a very long fin, the effectiveness is typically defined as thus. Okay, but note that this is just the effectiveness of an individual fin itself. The real question is, what is the total effect? What you really want to know is how much heat transfer has been initiated now. How has heat transfer increased in total since it uses both the fin as well as the free surface where the fins have not been taking up area? Okay, so how do we calculate this? Well, the overall efficiency is defined as the unfinned areas plus the finned areas, or the areas of the fins themselves, divided by the surface area if no fins were present at all. And what a beautiful question a lecturer could ask about this. Right. That was a lot of information, but fortunately for you, there is a lot of information summarized in the textbooks in the form of tables as well as graphs in the textbook. So be sure to go over this and practice, practice, practice. Here are some more tables and more tables and more. And note that this is a graph that the student should be able to use. There are examples in the textbook that show you how to use this. So go over those examples for yourself. And obviously you can expect 1 or 2 questions about these. Now this is a very nice geometry which you can consider for a heat exchanger. Obviously it will increase a bit of fouling, alright, but think about how this would be manufactured, for instance. Alright, lastly, the textbook provides some useful information, some considerations in terms of designing fins. I've already mentioned a few, but firstly, consider triangular and parabolic shaped fins. They will typically use less material and therefore tend to be more efficient. The fin efficiencies tend to decrease with fin length, and you should understand why this is mathematically so. Thirdly, you must also consider how additional fin lengths impact on the performance of fins, and consider how this could be justified. So, for example, fins that cause the efficiency to drop below 60% are not usually economically feasible. They require too much material and you can't justify their costs. And lastly, the efficiency of most fins that are used in industry typically are above 90%. So fins tend to be very efficient. If you aren't sure what fins look like in real life, you can Google them, but also these pictures should give you some clarity. Or you can open up an electronic device, but be sure to put it all back together again and don't lose any of your screws. Let's go through a quick example here. So read through the problem statement and see if you can identify all the useful bits of information that would be important. So first off, you should ask yourself, what should I assume? And secondly, you should ask yourself, what is the geometry of the fin in question? And where can I source all the information with regards to the requirements? Select the right geometry that corresponds and look at all the variables with respect to the equations that are given to you. Okay, so these are the equations that I've come up with. This particular example makes use of Bessel functions. Okay, the Bessel functions I, which are functions of x, which is the length, that are you get these from the table in the textbook, which I'm going to show you now, which is why specifically I've chosen this example for you. So this is probably the most involved exercise that you are going to have to complete for this section of work. So quickly pay attention, keep your wits about you. Okay, but before we look at those Bessel functions, let's first just calculate the easier bits of information. So calculate m times L, and we calculate this to be 0.25829699786. Who cares? Just don't overkill the number with the number of decimal points. On that note, do not ever give decimals to Reynolds number. Reynolds number is a qualitative number. We will also come to grips with other qualitative numbers in heat transfer. The decimals aren't important. What is important is how do you interpret such numbers. Okay, right. Note the efficiency. Okay, so consider it. We first determine x in this case and then calculate x to be 0.3443. So x is equal to 4 times m times L divided by 3. All right, so, oh, it's not a length. It doesn't have units. My bad. I thought it, for some reason, I thought it had units of meter. All right. In any case, we go to the textbook. There are some tables for you, Bessel function tables, so just look out for them. They are labeled as such. This is the modified Bessel functions for the first and second kinds. There's a little asterisk there that you can read up as well. And we would have to obviously interpolate between e to the power of negative x times I0 and e to the negative x times I1. So the two Bessel functions I0 and I1 is what we want to calculate. And the e to the negative x times by I0 is given to us in the table. Here you can see it's 0.8269 and 0.6974 for the one Bessel function, and then the other one 0.0823 and 0.1368. Okay, so we want just I. So what do? We shuffle the equations and then we determine what the values for I0 and I1 are. And now we can compute very easily the fin efficiencies, or the fin efficiency, right? Just for one fin, which is 96.3%. And I would say this is acceptable. This is very high. So good on you, fin. We are also asked to calculate the heat transfer, and in this case, it is calculated to be 1.77 watt. And this is quite easy also to calculate. Lastly, and finally, we are asked to calculate the question of effectiveness. How effective is the fin? And what we end up with is that the effectiveness of the fins are 10.3. So in other words, the fins have increased heat transfer by 10-fold, and this is great. It's like we've increased the surface area 10 times. Okay. The last part of the work involves a similar concept where heat is being transferred through slightly more complex configurations. Here we make use of a shape factor that corresponds with a common configuration that one would typically find in practice. The use of these S factors are pretty straightforward. I'm not going to go into too much detail with you. And you will find that there are many tables that summarize different scenarios, different configurations for you. So take note of these carefully and make sure that you can select the most important one that applies. And with this, we end off the lecture on heat conduction. See you guys soon.